We stare into the noise. The dim smudges, the thin streaks of light, and the same feeling keeps coming back. Something here is too early, too massive, too organized. If it were just one oddball galaxy, we could shrug it off, a measurement error, a statistical fluke, some weird lensing effect. But when patch after patch of sky keeps revealing heavy, mature structures in an era that should belong only to tiny cosmic embryos, the question stops being academic. It starts to feel personal. If our sharpest look into the past is telling us that the first cosmic cities grew up much earlier than our map allows, then what's wrong? The map or the eyes? Did we misjudge how fast galaxies and black holes can grow? Did we underestimate how much raw material the young universe had to work with? Or did we miss something much deeper in our basic ideas of what space and time actually are? This entire puzzle is hiding inside an image that could easily have been just somebody's desktop background. Another pretty wallpaper in an endless feed. Right up to the moment when you don't swipe past it. You pause. You hold your thumb on the screen. Then suddenly you realize this quiet, almost forgettable frame might be the first hint that the universe itself is built on rules we haven't even written down yet, and that James Webb has only just started turning the pages. They built it slowly, almost nervously, as if they were assembling a one-of-a-kind glass castle that could never ever be rebuilt. On the ground, it looked almost ridiculous. A huge golden daisy made of hexagonal petals, folded up shields like someone had tried to turn a beach umbrella into origami. If you walked into the assembly hangar with no labels on anything, you could easily mistake it for a massive art installation, not a scientific instrument. Imagine a giant makeup mirror that someone scaled up to the size of a tennis court and then broke its surface into 18 perfect golden honeycomb cells. Each one of those petals had to unfold in space, swing out and lock into place with an accuracy measured in fractions of a human hair. No step outside and nudge it with a wrench. No second chances. One launch, one deployment. One slow, high-stakes mechanical ballet happening about 1 million miles from Earth. While the rocket was carrying it into the cold black nothing, it was folded up like a pocket knife. Then, day after day, it began to open. First, the sun shield emerged. Thin layers of silvery material stretching out into space like 5 enormous mirrored sails, each one larger than a full-size tennis court. That shield had one job: turn the telescope into a creature with 2 faces, one side, always toward the sun, the other, always in darkness, pointed into the deep, where temperatures plunged to numbers you see not in a weather app, but in the manuals for laboratory freezers. Then came the mirror. The petals of the golden flower slowly swung outward like an umbrella opened in extreme slow motion. Each segment moved on tiny actuators, barely shifting, millimeter by millimeter. If you imagine standing in a stadium, looking up at the jumbo screen, the precision they needed is like trying to line up separate pixels on that screen by hand. But the weirdest thing about this flower isn't even its design, it's where it hangs. L2 isn't an address with a zip code and a street. It's easier to picture an empty parking lot out past city limits, lit by a single street lamp. Most of the cars crowd closer to the center, staying in the warm pool of light, the normal orbits. James Webb is parked out near the edge of the lot, in that strange spot where the street lamps glow from the sun and the faint reflection from Earth nearly cancel each other out. It's like the one car left in the exact place where there's just enough light to see the road, but not so much that everyone else's headlights blind your view. From that cold, stable shadow, it looks out with such sensitivity that next to it, our old Hubble Space Telescope feels like a nearsighted romantic. Hubble mostly worked in visible light, the same band our eyes use. It gave us the iconic nebula shots, starbursts, those dramatic pillars of gas that ended up as posters and laptop wallpapers. Hubble was like a person with a really good pair of binoculars, standing on top of a mountain. James Webb plays a different game. It sees in the infrared, in wavelengths that have been stretched by the expansion of the universe, light that started out as something our eyes could see, but has been pulled into long, warm whispers from the past. This isn't a binocular. It's night vision for the cosmos. If Hubble could pick out a street lamp on the other side of town, James Webb is trying to spot the faint flicker of a single candle in another city, through haze, smog, and glass. We built this machine expecting it to confirm our origin story, to tighten up the dates, clean up the margins, polish our model into something you could safely print in a textbook. But the moment its golden eye opened into the dark, it started sending back frames, after which the story itself began asking us uncomfortable questions. If you tried to compress the entire history of the universe into a single year, the Big Bang would happen exactly at midnight on January 1st, not as a loud firework in the sky, but as that impossible moment when out of nothing, space appears, time appears, and a churning, unbelievably dense plasma explodes into being. The very first fractions of a second in this cosmic year would be like the first fractions of a second on a New Year's clock in January, so extreme that we can barely even imagine them. They simply don't look like anything we know from experience. During the first few minutes of this year, the universe is like a newborn taking its very first breath. Out of a hot particle soup, protons and neutrons snap together to form the lightest nuclei. But real atoms are still far ahead. Everything is too hot, too dense. Light keeps crashing into matter and can't travel freely even an inch. Only around the end of our imaginary June does the temperature finally drop enough for electrons to stick to nuclei and form the first neutral atoms. The radiation that used to be trapped is suddenly let loose. Billions of years later, we detect that leftover glow is the cosmic microwave background, the oldest photograph of the universe as a baby. After that, a strange era begins, the one cosmologists call the Dark Ages. In our one-year calendar, it's a long, seemingly empty stretch of months where nothing obvious happens. Space keeps expanding, gas keeps cooling, and gravity slowly gathers slightly denser patches of matter, like invisible fists closing around handfuls of fog. There is almost no light. The sky of that era, if we could stand there and look up, would be blacker than any night sky on Earth. Real starlight doesn't turn on until near the end of October. Somewhere in the emptiness, clouds of hydrogen collapse. Nuclear fusion ignites, and darkness is pierced by the first ultraviolet lamps. The first stars, they live fast and die violently, exploding in supernovae and scattering heavier elements, carbon, oxygen, iron. From that debris, someday planets will be made, bodies, air, us. The first small groups of stars gather into miniature galaxies. You can think of them as the first villages on a blank continent. A few houses around a square, crooked dirt roads, zero infrastructure. Over time, these little galaxies collide and merge, growing into bigger cities. Highways appear. The filaments of the cosmic web, where more matter flows than anywhere else. This is how the large-scale structure of the universe is born, huge clusters of galaxies, with enormous voids stretched between them. By the end of December in our cosmic year, the stage is set with everything we're used to seeing. Giant spirals like the Milky Way, elliptical monsters, clusters where thousands of galaxies orbit in a shared gravitational grip. Somewhere out on the outskirts of one such spiral, on the very last day of the year, in the final seconds before midnight, a thin disk of gas and dust appears. The material that will become the sun, the earth, and our entire local drama. Classical cosmology lays out pretty clearly when each of these key pieces is supposed to show up. There is a construction schedule of the universe, when the first light switched on, when the first village is formed, and in which eras the first cosmic megacities were supposed to rise. That schedule is exactly what the James Webb Space Telescope was supposed to fine-tune. Scientists expected it to peer into the early months of the cosmic year and show us tiny, awkward galaxies. Small, lopsided, barely assembled, with stars scattered chaotically. No clean disks. No elegant spirals, not much mass. In that era, the universe was supposed to be just learning how to build cities, first houses, first streets, first lonely streetlights. To reach those times, we have to exploit one basic property of light. Light is fast, but not instantaneous. Even from the sun to the earth, it takes light about 8 minutes to arrive. When you look at the sun through proper protection, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. The moon is already a second and a half into the past. Nearby stars, years. Distant galaxies, billions of years. On top of that, the universe has another trick. Space itself has been expanding all this time. Light waves stretch out like a drawing on a balloon as it's being inflated. The farther away an object is, the more its light is stretched. Its spectrum shifts toward longer wavelengths, toward red and beyond, into the infrared. Cosmologists call this redshift. The bigger the redshift, the farther away the galaxy, and the deeper into the past we're looking. In a sense, redshift is our way of writing dates on the pages of the cosmic calendar. A galaxy with a small redshift belongs to late autumn. A galaxy with a big redshift lives in early spring, almost January. So when James Webb finds an object with a very high redshift, it's as if it's saying, look, I found light from something that happened in the first weeks of our imaginary year. And that's where the calendar starts to crack. In the slots where the schedule says there should only be tiny villages, James Webb shows us the lights of megacities. Instead of small, shaky structures, it's spotting objects that, based on our estimates, contain as much mass as today's large galaxies. Where we expected hastily assembled clumps, we find compact, dense cores, as if they've already had time to build downtowns with skyscrapers. In standard astronomical language, it sounds like this. Candidate galaxies at very high redshift look too massive and too evolved for such an early age of the universe. In human language, it's like opening your calendar to April, when it's supposed to be mild, quiet shoulder season, and finding New Year's Eve there. Fireworks, Christmas trees, crowded streets at midnight. We expected to see a universe still babbling its first words. Instead, we're catching someone who's already writing novels. And James Webb is not handing us just one weird, isolated photo. It's delivering a stack of them, on each one, its own adult galaxies at an age when they're supposed to be barely learning the alphabet. Of course, you can try to explain some of this away with caveats. Maybe the light is distorted by dust and our mass estimates are off. Maybe gravitational lensing, where massive objects warp space-time and act like magnifying glasses, is making some galaxies look brighter and bigger than they really are. Maybe there are selection effects in the sample, and some of these candidates will turn out to be something else entirely, once we collect better data. But the deeper James Webb digs into this early part of the cosmic year, the clearer it becomes. This isn't a one-off mistake. It's a systemic signal. Galaxies that look too grown up too early, they don't all sit in one patch of sky. Don't come from a single survey, or one team using one method. They show up in different programs, with different techniques, run by different groups. Our neat little scale of when things appeared starts behaving like a badly printed school calendar, where holidays and weekdays got shuffled. Some dates are shifted, some events spill onto pages where they don't belong. The universe we treated as a carefully planned construction project starts looking more like a city, where someone quietly hit the fast forward button. And then the question becomes much sharper. Then did we misjudge a couple of galaxies? If the first cosmic cities appeared earlier than they were supposed to, what does that say about our equations? Are we wrong about how fast matter can clump together? Do we still misunderstand the role of dark matter and dark energy in speeding up the growth of structure? Or is the problem deeper? Maybe we're not even marking time in the right way for the cosmos. If the universe's calendar starts breaking down on its very first pages, then in what other chapters are we in for surprises we don't even have names for yet? When you look at a single strange object, it's easy to shrug and file it under exception. Space is big, measurements are tricky, somewhere the data could have glitched. But the more James Webb peels back the early sky, the less this looks like a one-off error and the more it feels like a pattern. We imagined a calm, orderly universe. Instead, it resembles a city filled with things clearly ahead of their time. Imagine a tiny town on the side of a highway, a few one-story houses, a small store, a dusty square. And right in the middle of all that, a 40-story glass skyscraper with elevators, underground parking, and air-conditioned offices. It doesn't just stand out, it breaks the logic of the place. To build something like that, you need an entire construction industry, money, specialists, years of work. None of that exists in the village, yet the skyscraper is already there. That is roughly what some of the galaxies James Webb is finding look like in epochs where, according to our calculations, the universe should barely be trying to put up its first two-story houses. Instead of a small clump of stars, you see a compact but very massive object that, by its brightness, by its estimated mass, by its density, looks much more like the seed of a modern megacity than a dirt road on the outskirts of a brand new settlement. In another case, the image doesn't just show a single building, but an entire district, a group of galaxies already stretching toward one another like cars converging on downtown at rush hour. Between them, you can already see hints of matter streams, the future highways of the cosmic web. Yet if you check our notional calendar, this is still only the very beginning of spring. The map says there should be just scattered houses here and a footpath where the future freeway will go. Instead, we're staring at a fully sketched ring road. Then there is a third kind of surprise, even more audacious. Sometimes in these early epochs, James Webb finds quasars, insanely bright beacons powered by supermassive black holes in their centers. That's like walking into a first-grade classroom and finding a student calmly defending a PhD in theoretical physics. You expect to see a child who has just learned the alphabet, but instead you get an adult juggling equations that graduate students struggle with. Before these observations showed up, our picture of black hole growth was, overall, reasonably tidy. Some stars end their lives by collapsing and exploding. The leftover cores become black holes with stellar masses, say, a few times the mass of the Sun. Those seeds can grow over time, pulling in gas, consuming nearby stars, colliding and merging with other black holes. The process is slow, like building up wealth in a bank account, a few percent gain every cosmic year, a couple of lucky investments, one or two big mergers, and over billions of years you can, in principle, end up with a monster weighing millions or even billions of solar masses. It sounds plausible, and in the later ages of the universe we really do see such monsters sitting at the centers of galaxies. They obey certain relationships. The more massive the galaxy, the more massive the black hole at its core. It all looks like a long evolutionary growth story. The problem is that James Webb, looking into very early times, finds objects whose central black holes already appear, based on current estimates, to weigh billions of solar masses, even though the universe at that point has only lived through a few 100 million years. That's like checking the balance of a brand new bank account and seeing a number that realistically could only have been accumulated over centuries, even though you opened it last week. Astrophysicists do have accelerated scenarios they can reach for. You can assume that in some regions there was much more matter than average, and black holes there grew at the maximum possible rate, almost without pauses. You can allow that the first collapses didn't produce black holes of a few solar masses, but direct collapse black holes tens of thousands of times the mass of the Sun right from the start. You can add intricate feedback effects between radiation, gas, and dark matter. But even if you turn on all those turbo modes, some of the objects James Webb is flagging still look uncomfortably mature for their ridiculously young age. It's that same feeling of a skyscraper in a village, only now the village is the early universe, and the skyscraper is a black hole that by all rights should still be a child. On the screens in front of the scientists, there are spectra, graphs, sky maps. In labs and offices around the world, that all turns into the same very human scene. A room whose walls are plastered with printouts. Here, colorful blobs from deep fields where James Webb has pulled out barely visible drops of light. There, tables with redshift, mass estimates, error bars on the whiteboard equations. Arrows, more arrows, sticky notes saying check, too bright, lensing, dust. In that room, you keep hearing the same lines, reshuffled in different combinations. One voice says, "We just underestimated the growth rate." Conditions in the early universe must have been so extreme that galaxies and black holes could assemble much faster than we thought. We need to recalculate the models, add aggressive accretion, revise the initial condition. Another voice pushes back. If we start sprinkling accelerators everywhere, we're going to turn the model into Swiss cheese. It won't be a predictive theory anymore, just a collection of patches. Maybe the problem is deeper. Maybe the very shape of our equations is wrong for these early epochs. A third voice cautiously adds, "Look, our sample is limited. We always see only the brightest objects, because those are the ones the telescope can actually pick up. This is selection bias. Maybe James Webb is just picking out the honor students. In every class there's one kid who reads faster than everyone else and can solve adult problems. We're looking at those record setters and drawing conclusions about the whole class. plus dust, plus lensing. We have to be careful. This scene plays out again and again in different variations. The same set of arguments, only the names on the badges change. The institute logos on the coffee mugs are different, and the diagrams on the walls are local, not identical. But the essence is the same. Every new weird object forces you to bend the line on the plot just a bit more, tweak the caption under the equation, add another parameter to the simulation. If the anomalies were isolated, life would be simpler. You could say, here the telescope caught an especially strong lensing effect. There dust fooled our brightness estimate. Here we mismeasured the redshift. But the data are not coming from one corner of the sky. Different teams, different surveys, different data reduction pipelines, and still, again and again, galaxies pop up that are too big too early, along with black holes that refuse to sit on the usual growth curve. At some point, it starts to feel less like fixing a smudge of paint and more like trying to keep up with cracks in an old house. First, you patch the plaster in one corner, a month later, in another. Then you notice the doors don't close quite right anymore. Eventually, you have to admit, the problem isn't the paint. The geometry of the building itself is shifting. That's how it is here. Every time a new James Webb observing program delivers another suspicious object, we pull out our cosmological blueprint, the standard model, and try to figure out where to pencil in one more column, one more beam, so the structure doesn't collapse. We raise the ceiling on how massive early galaxies are allowed to be, speed up black hole growth timescales, add clever interaction terms with dark matter, and for a while the drawing lines up with reality again. But the cost of that agreement keeps going up. The model has to be bent harder and harder. More and more parameters are tuned after the fact to explain what we've already seen. There's less and less room left for clean, advanced predictions. At some point, a nasty feeling creeps in. We're no longer holding a map of the territory. We're holding an excuse. A map is supposed to help you find your way, not explain why you got lost again. If every time we try to describe new galaxies and quasars, we have to redraw lines and erase old ones, maybe the issue isn't that we got a few details wrong. Maybe we're looking at reality from the wrong angle. Then the old question about early cosmic cities becomes just the ground floor of a bigger problem. If the megacities showed up earlier than our schedule says they should, what else in this universe is built in the wrong place, at the wrong time compared to where we've been drawing it? Where else is the foundation cracking, while the outside walls are still neatly painted? And how many more skyscrapers and villages does James Webb have to show us before we admit that maybe the time has come, not to patch the plaster, but to take a hard look at the blueprint itself? Add one more uncomfortable layer on top of that. It isn't just about the mass and size. In some of the early galaxies James Webb is flagging, the chemical makeup of the stars also looks suspiciously mature. In principle, the very first generations of stars should be made almost entirely of hydrogen and helium, the original building blocks of the Big Bang. Heavier elements like carbon, oxygen, silicon, and iron only appear after several generations of stars are born, live, and explode, enriching the surrounding gas. If you're seeing light from a very young galaxy, you expect raw material. But the spectra of some of these objects whisper that in these regions, not one or two, but multiple waves of star formation may already have come and gone. There are enough heavier elements there to start forming complex molecules, dust, and potentially future rocky planets. It's like walking into a school that just opened and finding a library whose shelves are already packed with dissertations, plus a dozen graduates who've somehow had time to become professors. Another front of weirdness is the structure of the very earliest neighborhoods of the universe. James Webb is finding protoclusters, embryonic versions of the big nodes of the cosmic web, in places where we expected mostly lone galaxies. Picture a planning map where city designers carefully draw, here will be a village, here a small town, and here, in 100 years, a major metropolitan hub. Then the satellite images come in, and they show overpasses, bridges, shopping malls already under construction, exactly where the future megacity was just a dotted outline, as if someone started the build decades before the official groundbreaking. Sure, you can say, we're simply detecting the most favorable, densest, best located patches. The universe is big. Somewhere there will be ultra-efficient hotspots of growth. But the more of these hotspots James Webb finds, the harder it becomes to treat them as mere lucky exceptions. At some point, the statistics turn against us. There are too many gifted kids in this class for them to be rare outliers. Against this backdrop, the tone of scientific discussion shifts. At first, the papers are careful, with phrases like unexpectedly high mass or requires further investigation. But over time, titles increasingly contain words like tension, crisis, challenges, standard model. To an outsider, it might sound like headline drama, but inside the community, it's a very specific signal. The trusted framework is starting to stall. It's like opening the manual for a precision watch and finding a note at the bottom. Under some conditions, this watch may run fast or slow by several weeks. Yet still, science has a stubborn habit. It will fight hard to salvage the parts of its worldview that still work. Nobody throws out the foundations just because one telescope found a couple of odd blobs. Before we abandon an old map, we'll twist it, fold it, try to line it up with new roads, draw fresh lines over the old ones, and that's healthy. Without that kind of conservatism, we'd be rewriting fundamental theories every month. The real question is different. At what point does the number of patches become evidence that the fabric itself is no longer holding its shape? Gradually, the feeling of exception gives way to the feeling of symptom. Overmassive early galaxies, black holes that grow too fast, structures that are too organized where there should be scattered construction sites, hints of chemical maturity arriving suspiciously early. All this starts to add up. It's like looking at an X-ray. At first, the doctor sees a single shadow and says, "We should retake this." But when the new scan shows shadows in several places at once, the tone of the conversation changes, and then the main question becomes much broader than how early could the first galaxies appear. If the universe in its own teenage years is already displaying a level of maturity our models can't keep up with, then maybe the problem lies in how we're counting its age, its growth, and its development in the first place. We're used to a story where everything flows slowly and predictably out of the past. But what if the early cosmos wasn't just faster but qualitatively different from what we've been assuming? And if that's true, how many more hidden floors does this building have? Floors we haven't even tried to visit yet. When the familiar picture of the world starts to creak, science at its core always has two basic moves. The first is the most comfortable one. Adjust the parameters, nudge the growth rates a little where things need to speed up, tweak the fraction of dark matter so it helps galaxies form faster, rewrite the initial conditions just enough to make the story smoother. The second move is unpleasant. Admit that the whole time we've been solving the wrong problem. That's not just how cosmology works, that's how any complex system behaves under pressure. Imagine you're in charge of traffic in a big city. Your entire life is maps, charts, and sensors at intersections. You know where traffic jams usually form, at what hours downtown gets clogged, which detours people choose when a major bridge is under repair. Your model of the city is neat, reproducible. It does a decent job predicting where things will lock up in the morning. And then, one day, something strange starts happening. Places that should be wide open according to your data suddenly clog with traffic. Cars begin bunching up on side streets that were never considered main arteries. Meanwhile, a couple of your classic bottlenecks are mysteriously empty. At first you think, accident, road work, bad sensor data. But day after day, the pattern repeats. Traffic jams form where they shouldn't and vanish where they usually linger for hours. You grab your old schematics and start nudging them. You add a correction factor to the flow of cars in the eastern districts. You redraw signal priorities. You retune timing cycles on a few lights. For a short while, the model works again. Then, a week later, it collapses. People are moving in ways your formulas don't account for. Only after a while does the obvious idea finally click. There are new navigation apps. Someone rolled out a service that routes drivers through back alleys, narrow side streets, old service roads that don't even exist on your map. For the people behind the wheel, it's just a convenient arrow on a screen. For you, it's an invisible network of roads your model doesn't even know is there. You keep calculating based on the old city, but the cars have already switched to a new one. Something similar is happening with the early universe right now. We've been acting as if we know all the roads matter can use to move and clump together. There's gravity, pulling everything toward everything else. There's dark matter, that invisible mass that adds extra pull where normal matter isn't enough. There's the expansion of space, pushing everything apart. We built huge, beautiful simulations where slightly lumpy early gas slowly turns into filaments of the cosmic web, nodes of clusters and galaxies. When James Webb started showing us systems that are way too massive and way too mature in epochs where they weren't supposed to exist, the first move was predictable. Let's adjust the parameters. Let dark matter behave a bit differently at early times. Let the initial density fluctuations be slightly stronger. Add more efficient cooling for gas so it falls faster into gravitational wells. Turn on scenarios where the first black holes are born not from single stars, but as large seeds, tens of thousands of solar masses right out of the gate, ready for a growth spurt. These attempts are honest. They don't come from a desire to save face, but from the inertia of the scientific engine. You squeeze everything you can out of known physics before you touch the foundations. Some researchers go further and suggest changing the usual equations of gravity, making them scale-dependent. On very large distances, gravity might behave slightly differently from what we measure inside the solar system. Ideas like that have lived for a long time at the fringes under the label of modified gravity. Now they're quietly stepping back into the light. Others are building alternative scenarios for structure formation. Maybe the early universe hosted interactions we don't know about yet. Maybe dark matter doesn't just sit quietly in its halos, but can collide with itself, flow around, and speed up the formation of dense knots. It's like taking your familiar city map and sketching in new overpasses, tunnels, freight lines, claiming they were always there, we just hadn't paid attention. But the longer this goes on, the more it starts to feel like we're trying to explain strange traffic, not wanting to admit that someone is using a completely different routing system. We're forcing the old map to fit the new patterns of movement instead of asking, has another invisible layer of control appeared above the city? That's where a different line of conversation quietly enters. For now it speaks softly, cautiously, without dramatic slogans, but the meaning is simple. Maybe we're misunderstanding the logic of reality itself. We've been staring at the universe as if it were a giant stone cathedral built from matter, fields, and forces, but it might be much closer to something else. A computation. The idea that the universe computes itself in some sense isn't brand new, and it isn't stolen from sci-fi. When physicists look at black holes, they notice something strange. On the surface, a black hole is just perfect darkness, a region from which nothing can escape. But the equations insist it has entropy, measure of how many possible internal states it can be in, and that entropy is not proportional to the volume, as we'd expect for normal objects, but to the area of the event horizon, the imaginary surface separating here from never again. Translated into a simple picture, that's like a safe you judge not by how much space it takes up in the room, but by the size of its door. It's as if everything that can happen inside is somehow written on that door. From there, a strange conclusion grows. Information about what's inside doesn't have to sit inside in the way we're used to. It can be encoded on a boundary. That leads to the so-called holographic principle. In some sense, a three-dimensional world can be fully described by information stored on a two-dimensional surface, like a volumetric film that's completely encoded on a flat screen. We walk around inside the auditorium, while the full script of the play is written on the walls. These ideas live far from everyday life. They live in papers full of dense math. But for us, the technical details aren't as important as the tone. More and more physicists are seriously talking about the possibility that the basic layer of reality might not be matter and fields themselves, but information about them. How many states are possible, how they're stored, how they're transmitted and processed. Reality is a process of data handling. If you look at the universe from that angle, those early anomalies in James Webb's images shift the emphasis a bit. We stop asking only how did these galaxies grow so fast? And why did these black holes accumulate so much mass so early? We start asking, could there be some extremely efficient process of organizing information happening on a deeper level, something we only glimpse through its material footprints? Let's go back to the nighttime city. Seen from orbit, you get a map of lights. Some neighborhoods are bright and dense. The centers, highways stretch out from them as luminous threads. There are dark patches, parks, industrial zones, water. If that's all you know, you can spend a long time arguing about why some areas glow more than others and how people gradually settled the land. But if you know that beneath all this there's a network of roads, power lines, fiber, server farms, financial flows, data centers, you understand the distribution of lights isn't just a pretty pattern. It's a footprint of a huge system processing energy. goods, signals, money, decisions. The cosmic web, as astronomers see it, is also a map of lights. Only instead of street lamps, you have galaxies. Instead of highways, you have filaments of dark matter, along which gas and stars stream. We used to treat that pattern as a natural consequence of gravity acting over billions of years. No special plan, matter pulls matter, occasionally outruns the average expansion of space, and eventually knots and voids appear. But if the universe, in some sense, records its states on boundaries, if black holes and horizons are hinting at a finite information capacity, if the dynamics obey not just equations of motion but also rules of data storage, then the distribution of galaxies can be seen as a way of packing information, as the way a huge system encodes and redistributes its resources. That doesn't mean someone drew the network on purpose. It doesn't mean there's a programmer floating above the cosmos flipping bits. This is not about a director or an author of the script. It's about the possibility that natural laws behave like algorithms, step by step, turning one state into another under specific rules, minimizing entropy here, increasing it there, rebalancing structure. The way a computer rebalances load across servers in a network. From that point of view, those early, overly mature galaxies and fast-forwarded black holes might not be rule breakers, but features of how the universe solves its own organization problem. Just like search or optimization algorithms sometimes create hotspots where the solution overshoots and jumps too quickly toward a local maximum, we may be looking at cosmic hotspots where structure condenses far faster than our smooth, averaged-out simulations would suggest. We see the result, enormous cosmic objects, and think this shouldn't happen because in our relatively reply models, everything grows slowly and gently. But under the hood, there may be a more intricate rule at work, one we haven't decoded yet. It's possible that what we call dark matter and dark energy are not just another kind of stuff, but manifestations of a deeper layer of code that dictates how structures are allowed to form and spread. We see only the pixels, galaxies and clusters. We don't see the program that against that backdrop is boosting some regions and damping others. That sounds dangerously close to science fiction, and this is exactly where the line matters. Science is not saying the universe is literally a PC in someone's basement. It's saying, much more cautiously, our best descriptions behave as if reality is a process of information processing. Maybe we should look at weird data not as broken numbers, but as hints that the algorithm is more complex than we assumed. Then the question James Webb poses with its images changes shape. It's no longer only why are there skyscrapers in the early cosmic village. It becomes, maybe the village itself is just one level at which a far more complex system shows through. We see only the lights on the map. The actual logic of routes, outages, and restarts hides in a layer we can't directly access. And if the universe really is closer to a computation than to a stone cathedral, we're left with the strangest but unavoidable question. What exactly is it computing? Imagine an ordinary apartment building. At the bottom you have the parking level in the basement, full of pipes, cables, boxes, old bicycles. Above that are the residential floors, hallways, doors, kitchens, televisions. Higher still, there's a technical level, the roof, antennas, satellite dishes, cables disappearing into the dark. Most residents live on one or two floors and rarely think about how the whole building is put together. Everyone has their own little territory, an apartment, a stairwell, an elevator. We're used to treating reality the same way. There's one three-dimensional world plus time. Tables are solid, people walk down streets, planets orbit stars, galaxies fall into clusters. All of that is one big, understandable floor. We live on it. Build our theories, measure motions, and try to lay events out on a neat timeline. Earlier and later, past and future. It feels like the only real complexity is measuring who runs how fast along that straight line. But physics has been hinting for a long time that our floor might not be the only one. Below and above there are other levels that follow their own rules. We just don't look there very often. On the very bottom, in the basement so to speak, lives the quantum world. There are no familiar objects there. Instead of balls and planets you get probability waves. Fields that can be in several states at once, particles that act sometimes like points and sometimes like waves, superpositions where something is here and there at the same time until we look. It's a strange space where everyday logic breaks. We know it exists because of experiments, but we don't feel it in our bones. Above that is our ordinary classical world. Tables, cups, bricks, bodies. Here, the familiar rules hold. If you push a ball, it rolls. If you let go of your keys, they fall. If you flip on a lamp, the room gets brighter. We live on this floor and call it reality. Higher still is the cosmological level. Scales so large that individual stars and planets blur into the background. Up there, the equations describe the expansion of space, the growth of the cosmic web, the fate of entire galaxy clusters. We see that floor through telescopes and space missions, but we treat it as something distant hanging over our heads. Normally, those floors stay neatly separated. Quantum weirdness is tucked away in the micro realm, where it doesn't seem to touch daily life. Cosmological effects are too slow and too huge to matter when you pour a cup of coffee. We live in a narrow band between the basement and the roof and call that band the real world. Now imagine that somewhere in this building there's an elevator with a glass wall. And at some point that elevator doesn't stop exactly at a floor. It stops between floors. Part of what you see outside is still your familiar world. The rest already belongs to the neighboring level, where everything is built differently. The view through the glass starts to look strange. Pieces of objects seem familiar, and other pieces look like they belong to a completely different building. You can think of the James Webb Space Telescope as that glass elevator that has come to a halt between floors. We assumed it would just drop us down into the basement of cosmology, the very early universe where the classical picture is still under construction. But the more it looks, the more it seems like it has caught a zone where different modes of reality haven't fully separated into distinct floors yet. The quantum world has been showing us one particularly awkward trick for decades: long-distance connectedness. In experiments, you can create a pair of particles whose properties are entangled. Measure one, and you instantly know what's going on with the other, even if it's far away. There's no signal outrunning light, but it feels as if there's an invisible thread between them. Einstein called it spooky action at a distance, and it bothered him a lot to feel how much that clashes with our familiar floor. Imagine two light bulbs in different rooms, or even in different cities. Each one has its own switch. You flip one switch, and both bulbs turn on. You flip it off, and both go dark. You check the wiring, you check the grid, you install sensors. There's no direct connection. But every time one bulb decides to be on, the other behaves exactly the same way, even if there are thousands of miles between them. Quantum theory says, in the microscopic world, behavior like this is not only possible, it's routine. We comfort ourselves with the idea that this weirdness gets averaged out and disappears when you build something big: molecules, dust, rocks, planets. But what if at some level that connectedness never fully goes away and instead gets built into the structural beams of the house itself? Then our classical floor isn't truly independent. It hangs on invisible but strong ties to the quantum basement in the cosmological roof. From the other side, the cosmological floor is not as simple as we'd like either. The cosmic web is not just a random sprinkle of galaxies, it's a network. Galaxies are the nodes. Dark matter is the invisible frame, binding them with filaments. Gas flows along those filaments. Stars are born where the lines intersect. Black holes sit in the centers and recycle some of the matter back into the environment. Look at it as a picture, and it's easy to see just a beautiful chaos. Look at it as a map of connections, and it starts to resemble a gigantic neural network. In a regular computer, a neural net is a structure where each node receives signals from others, applies some rule, and sends the result on. Over time, the network learns. Certain links strengthen, others weaken. It gets better at recognizing faces, translating languages, finding patterns in data. Its mind is not a single transistor, it's the whole web of connections taken together. You can very cautiously imagine that something similar is happening with the cosmos. Not in the sense that the universe is an AI someone booted up on a server, but in the sense that the layout of galaxies, filaments, and voids is not just the outcome of gravity, but also the way the system redistributes its resources and information. Nodes that grow too fast look like hotspots of computation. Voids are like regions where the load is temporarily minimal. By peering into early times, James Webb doesn't seem to be looking at the first houses on an empty field. It's staring at the stage where the network itself is forming, where you can still see how the first cables are being laid, where traces are still visible of how the quantum basement and the cosmological roof are negotiating the rules. If you allow yourself to step a little sideways from strict physics and switch the imagination on carefully, you can picture the different layers of physical reality as floors in a huge mall. On the first floor there's the supermarket, carts, shelves, checkout lines, noise. On the second floor there's a movie theater where people sit in the dark watching glowing screens. On the third there are technical rooms no regular customer ever sees, cables hanging from racks, compressors humming, server lights blinking. A shopper who only ever visits the supermarket can live their whole life without realizing there's a theater above them. Someone who spends their time at the movies rarely thinks about the machinery needed to keep the projectors running and the air cool, but it's all the same building, just different levels. And sometimes, if you get stuck in the elevator between floors, you suddenly hear both the low rumble of refrigerators below and the muffled movie soundtrack above. The real world may be arranged the same way. Our familiar supermarket of classical physics sandwiched between a noisy quantum basement and the quiet but powerful mechanical floors of cosmology. Quantum entanglement stretches threads up from below, the cosmic laws of expansion and curvature press down from above. In daily life we only hear our own floor. But in the most sensitive experiments, and especially when we watch the early universe, the elevator seems to jam in the middle. We start seeing weird combinations that don't fit into any clean mode. Maybe that's how we should look at some of James Webb's 2 grown-up galaxies. Not as objects that break our laws, but as regions where different sets of laws overlap. Places where quantum fluctuations, classical gravity, and the global dynamics of an expanding space all line up briefly and produce results that seem impossible on our floor, but perfectly natural on the scale of the entire building. There are scientists whose careers are consumed by one such oddity. Picture an astrophysicist who spends 20 or 30 years on a single anomaly. Maybe it's a strangely cold patch in the cosmic microwave background, a region of the sky where the ancient radiation is a bit more dropped out than theory expects. Maybe it's a massive cluster of galaxies behaving as if something invisible is pushing it harder than usual. On paper it all looks like careful plots, error bars, statistical tests. In a human life it's one question on repeat: what am I missing? This person changes institutions, cities, and students. They update simulation codes, add new parameters, rewrite old programs. Sometimes it seems like the anomaly is about to disappear, smoothed out by better measurements or a newly recognized effect. Sometimes it feels like there's a whole new layer of physics hiding behind it. James Webb delivering fresh weirdness doesn't calm people like that down. It's as if the telescope is whispering, "You're not alone." Other parts of the building aren't lining up either. To get a feel for how layers of reality might behave if they were closer to everyday life, try a thought experiment. Imagine you live in a normal apartment. In the morning you walk into the kitchen and turn on the kettle. Everything is familiar, but from time to time you start noticing small oddities. Maybe the lamp in the room turns on a fraction of a second before your finger actually hits the switch. Maybe the elevator sometimes drops you off on your floor a split second before you feel the jolt of starting. Maybe in the supermarket you visit every day, the arrangement of products seems to reshuffle itself exactly when you turn away, as if it were adjusting to your path. At first you'd blame fatigue, memory, coincidence. But if there are more and more of these episodes, at some point you'd have to admit there might be another floor under your familiar one, and you're bumping into it somehow. Maybe someone or something is editing the script, just a tiny bit ahead of your footsteps, not because there's a conscious meddler, but because 2 layers of reality occasionally come too close together. In the cosmos, we don't see shelves crawling around a supermarket. But we do see the large-scale structure of the early universe looking as if something already knew where the most massive structures should appear. As if the universe's own neural network anticipated regions where it would make sense to invest resources. In scientific language that shows up as correlations, fluctuations, power spectra. In metaphorical language, it feels like cosmic coordination. You can imagine floors where time runs differently. Not in the fairy tale sense of a magic portal, but in the sober sense that each floor of the building treats past and future in its own way. In the quantum basement, Time may not behave the way we're used to at all. Interactions and probabilities matter more than a clean before-after ordering. On the cosmological roof, time stretches and blends with the expansion of space. We live in between, on a middle floor where clocks are still good enough for everyday life. But the extreme levels still distort the overall plan of the building. In that case, what we call galaxies might be nothing more than pixels in a much larger image that only makes sense when you step back and look at the building as a whole. A single square on a screen carries a tiny piece of data, but real meaning only appears when you see the full frame. By zooming in again and again on tiny patches of sky, James Webb is effectively showing us individual pixels of an enormous picture. And the clearer those pixels get, the more you want to step back and ask, what image is this pattern trying to form? We don't know if the universe actually has such a big picture. Science is careful. It sticks to what can be tested, measured, repeated. Everything else lives in the realm of hypotheses, speculation, and philosophy. But when a telescope we built to polish up an old picture suddenly starts revealing structural oddities on several levels at once, in mass, in maturity, in distribution, it's hard to shake the feeling that maybe it has caught more than a distant past. Maybe it has lit up a scene between floors. At that point, the building of reality we drew for ourselves stops looking flat. Beneath us is the quantum basement with its 2 lamps and different cities. Above us is the cosmological roof where space itself stretches and warps. In between is our everyday life, and somewhere in the middle, between floors, hangs a golden eye staring into a region where all of that hasn't fully split into separate levels yet. Maybe that's why James Webb's images feel so unsettling and beautiful at the same time. We thought they would show nothing more than a baby universe. Instead, faint outlines of something bigger shine through them. As if in walls we thought we knew, the shapes of a hidden architecture suddenly appeared. And maybe this isn't just bad math or statistical quirks, but the first very careful reminder that our house of reality has more floors than we were taught, and James Webb has cracked open a door on the landing between them. If you follow that line a bit further, you can look at one more subtle detail, how we ourselves perceive time. On our floor, it feels like a straight line. Yesterday, today, tomorrow, we build biographies, chronicles, grids of dates. But even in ordinary physics at high speeds or in strong gravity, time begins to bend. Clocks on a satellite and clocks on the ground tick at slightly different rates. For us, those differences are tiny. You need atomic clocks to even notice them. Across the scale of the universe, though, such tiny mismatches grow into real distortions. Now imagine that every floor in this cosmic building has its own sense of time. In the quantum basement, the outcome of a measurement can seem to reach back into what was considered possible moments earlier. On the cosmological roof, the fate of entire clusters isn't set just by their past, but by the overall expansion trend of space, encoded in equations across immense scales. We live in between, convinced that a minute is a minute and a year is a year. We measure the age of galaxies with the stopwatches of our floor and then act surprised when some of them seem to have fit too much in too early. What if James Webb is showing us a region where those different notions of time intersect, where our linear calendar doesn't quite apply yet, and purely quantum and purely cosmological time regimes haven't fully separated? In that case, too early maturity may be less a violation, and more a sign that we're trying to mark a boundary between floors with a ruler designed for only one of them. You can return to the neural net metaphor. When engineers inspect activity maps inside a deep model, they often see layers that light up together for specific inputs. One layer clearly tracks edges, another shapes, a third more complex objects. But there are also weird layers whose behavior is hard to interpret. They seem to latch on to some hidden, more abstract regularities that aren't just lines or objects. People call them bottleneck layers or latent space, a hidden space of features. What James Webb is doing faintly resembles probing that kind of hidden layer in the universe. We feed the system an input, a patch of sky, an early era, a set of wavelength. On the output side, we get unexpected objects that don't fit any simple, too small, too big, too early, too late category. They seem to live in some latent space of cosmic states for which we don't yet have a language. We only see their shadows on our familiar floor, mass, brightness, redshift, but not the structure of the hidden layer itself. That might be the most important part of the rethinking the telescope is pushing us toward. It's not forcing us to throw out the old laws overnight and declare the world a simulation or an illusion. It's doing something else. It's forcing us to admit that for a very long time we've mistaken one floor for the entire building. We built a neat picture of reality where quantum effects are conveniently stuffed into the micro world. Cosmological ones are pushed far into the past and future. And in the middle, our everyday world stands proudly on its own. Now there are holes in that picture. And through those holes we can see structures we didn't know were there. A few decades from now, we may look back at today's debates about early galaxies the way we now look at the first shocked reactions to the idea that the Earth orbits the Sun. Back then, it felt like the entire order of things was collapsing, that everything had been swapped around. In reality, we just discovered that the house we live in is far larger and more complex than what we see from our window. James Webb is not an answer, and not a verdict. It's simply a new elevator that, for the first time, stopped between floors and gave us a brief look through the crack between the doors. And now the real question isn't whether we should slam that crack shut, but whether we're ready to admit that this building has more levels and that we might actually be able to go higher. It's late at night. Outside, the street is empty, a few passing cars, that soft orange glow from a street lamp under the ceiling of the sky. In the room, there's only one real source of light, a screen. Maybe it's a laptop, maybe a tablet, maybe a phone sitting on the charger by your bed. And on it you don't have a show running, not a social feed, but a site people open much more rarely. It's showing images from the James Webb Space Telescope. You flip through them one by one, deep fields where every tiny dot is a galaxy, spectra that look like little colored picket fences, images of nebulae that resemble smoke or fire or stained glass windows. All of this is coming from places where there were no people, no Earth, not even the Sun. The screen is small. The whole universe fits diagonally into just a few inches. Your fingers pinch and spread the image, zooming into the frame. For a second, there's a very strange feeling. A private consciousness stuck in a dark room at night is trying to cram cosmic scales into a glowing rectangle. A microscopic eye is studying a labyrinth of layers of reality that has existed for almost 14 billion years, and it's doing it by swiping pictures. The first natural reaction to a contrast like that is fear, not necessarily panic, not necessarily something you can even put into words, more like a slow, sticky feeling. This is too big, too alien, too complicated. When you look at a map of skyscrapers in a nighttime city, you can still imagine yourself somewhere in there on one of the floors, but when you're looking at a map of the cosmic web, where a million galaxies are just a tiny point on a plot, your usual reference points vanish. Your built-in sense of normal scale breaks. Right behind it comes a second feeling, awe. Almost physical awe. At some point, you stop trying to fit these images to yourself and start doing the opposite. You fit yourself to them. Not me versus all of this, but I am a tiny part of all this that suddenly learned to look at the rest. And that's not just frightening, it's beautiful. It's like realizing you've spent your whole life in one room of a huge house, and now for the first time you've looked out the window and seen an entire city outside. Then, usually, a third voice kicks in. The skeptic inside you. It says, so what? We're nothing. A tiny lump of organic matter on a random planet, orbiting a random star. One day the sun will die, galaxies will collide, the universe will cool down, and no one will remember you or your problems. That sense of meaninglessness is the most familiar side effect of staring into space. The bigger the picture, the easier it is to erase yourself from it. At first glance, cosmology seems to just pour gasoline on that fire. Huge numbers, terrifying scales, talk about layers of reality, and a universe that might be computing itself for billions of years. If the universe is a multi-layered network that has been running its own code since the beginning, why should anything you do in your dark room with your laptop matter at all? But oddly enough, that kind of perspective doesn't shrink us. It puts us back in a place that might be far more interesting than the role of a random speck of dust. If you picture the universe as a kind of gigantic organism, then galaxies, clusters, and dark matter filaments are something like its skeleton and circulatory system. The laws of physics are its genetic code and biochemistry. The cosmic web is the network of vessels that carry matter and energy. In a body like that, there ought to be sensory cells, the ones that gather information about what's happening and pass it on. We look a lot like those cells. Every time someone opens a James Webb image, reads a paper about early galaxies, or quietly asks, "What does this all mean?" The universe is, in a very real sense, observing itself, not through abstract equations, but through a specific human gaze that can feel fear, wonder, and meaning. Before telescopes, this organism's sensory toolkit was very limited. A bit of infrared feeling in rocks and planets that can heat up and cool down, a bit of chemical sensitivity in simple molecules that react to light and warmth, a bit of local memory in the form of impact scars and cracks on surfaces. Then eyes appeared in living things. Animals, humans. Then glass lenses that amplified vision. Then Hubble, which learned to see nebulae as cities. Now James Webb, a new sensory organ. This organism has grown literally in the final seconds of its cosmic year in order to finally look back at its own beginnings. We built it for ourselves. But in the big picture, it's the universe finding a way to see its own infancy from the inside. In that picture, an observer is not random noise. The observer is part of the mechanism. If reality really does behave like some kind of computation, then observers are the nodes where information gets gathered and compressed. Different strands of the code meet in them. Memory, perception, prediction, choice. Without such nodes, the computation would be blind. That immediately brings up a heavy question. If all this is a computation and we're the nodes, do we actually have free will? Are we deciding anything, or just dutifully playing out a script written into the code, like a program running on a chip? On one hand, the honest answer is uncomfortable. Our freedom is limited. We can't violate conservation of energy, turn off gravity, or jump over our own mortality. Our thoughts, feelings, decisions are tied to a brain built out of the same atoms as stars. In that sense, we're fully embedded in the machinery. On the other hand, complex systems have a curious property. When you look at a program line by line, it feels rigid. Here's the condition, here's the loop, here's the result. But if the program is complex enough, it produces states you cannot predict by just eyeballing the code. Not because there's chaos, but because there are too many possible paths. That's how weather works, how economies work, how the brain works. The existence of general rules doesn't kill the unpredictability of specific outcomes. Free will on our floor of reality might be exactly that, built-in unpredictability. From the outside, you can describe us with equations and statistics. From the inside, we experience our choices as real. Both descriptions can be true at the same time, just on different floors of description. The quantum basement, the classical floor, and the cosmological roof don't cancel each other, they overlap. The next question cuts even deeper. Does a universe like this have any intention at all? Or is it all pure mechanics that just happen to accidentally generate beings who ask why? Science doesn't give a clean yes or no. It's good at saying this is how and this isn't how. It can explain that the Big Bang wasn't an explosion in empty space, but the birth of space-time itself. It can measure how fast the universe expands, how galaxies are distributed, how black holes behave. It can't measure meaning. That doesn't mean meaning doesn't exist. It means meaning doesn't live on the same layer as curvature of space and the density of dark energy. Meaning emerges precisely in those sensory nodes we're talking about. By default, it's always local. For some people, it's family. For others, work. For others, the search for truth. Helping others, making art. The cosmos doesn't write a goal for us as a line of code, but it does give us the conditions under which such goals can exist at all. Stable chemical bonds, long-lived stars, planets with decent climates, brains capable of storing memories and imagining futures. Why do we live in this particular layer of reality? Why not in a world where quantum strangeness is obvious at every step, where a glass of water is literally both full and empty at once? Why not in a reality where gravity is so strong that no complex structure ever has time to form? The boring answer might be, we could only appear in this kind of layer. If the whole house of reality is a multi-story building, humans are tenants of exactly those floors where long-lived, self-aware I can exist. On other layers we can only speculate about. There simply can't be any I at all. Where time behaves too chaotically, where energy dissipates instantly, where there's no persistent memory of states. There are no observers, no questions, and no late-night videos of someone staring at pictures of distant galaxies. From that perspective, the very ability to ask what does all this mean is already a luxury, not a fluke. but the result of the universe reaching a mode where higher-order layers, biological, mental, cultural, become possible. Yes, we're small, but we're unique in being able to understand our own smallness, and that's where a very particular mix of three states appears, without which any talk about the cosmos turns either into propaganda or into empty romanticism. The first is humility in the face of scale. Not a performative humility, but a quiet one. Admitting that we are not the center of the picture, not the crown of creation, not the main goal of the universe. That our theories are incomplete, our maps are crooked, and our eternal truths are easily overwritten by new data. Every James Webb image is a reminder. Reality is smarter than we are. The second is responsibility. Not in some high-flown sense, but in a very practical one. We are the first generation of living beings on this planet that knows about the cosmic microwave background, about the structure of the cosmic web, about how stars are born and die, about the possibility that the universe has layers we're only starting to glimpse. We are the first to see it this way. What we do with that knowledge, bury it in textbooks, weaponize it, or use it to keep our small civilization alive a bit longer, is on us. An organism that grows itself a new sense organ is responsible for how it uses it. The third is curiosity, maybe the most honest feeling of the three. The story is clearly not over. James Webb has only just begun working. There will be new telescopes, new missions, new theories. Some of today's anomalies will turn out to be simple mistakes. Some will grow into entire new branches of physics. Some will drift into philosophy. But the mere fact that we get to live at a moment when the universe seems to be lifting the edge of its own rug and showing that there's another layer underneath, that alone is a reason not to slam the laptop shut with a tired "we're nothing," but to turn the page. The night outside hasn't gone anywhere. The room is still just as small. The screen is still the same size, nowhere near a literal window into infinity. And yet, in this moment, infinity is looking at itself through that screen, through your eyes, your curiosity, your fears, and your attempts to find words. And it might be that this exact place, between the enormous and the tiny, between code and lived experience, between a house with many floors and one very specific apartment, is the layer of reality where we truly live. Imagine we're back in that same dark room again. The screen, the dim glow, the quiet outside the window. Somewhere at the very start of this story, there was just one image on that screen, a dark sky, a scatter of dots, a faint haze, one tiny pixel you could easily swipe past. But now that pixel no longer looks like an innocent wallpaper. You know that inside that blurry smudge there are hundreds, maybe thousands of galaxies. That each point could be an entire city of stars. That behind some of them hide monster black holes that somehow grew far too fast. That buried in that depth, you might be seeing the seam between different floors of reality we used to neatly separate into different textbook chapters. You're looking at the same image, but you're seeing it as the first frame of a movie, not the last slide of a presentation. Not as an answer, but as the setup. The James Webb Space Telescope has barely started working. The first deep fields, the first surveys, the first controversial mass and distance estimates, they're basically lab notebook sketches. With every new observing campaign, Webb will go back to the same patches of sky, refine the data, push deeper, pick out fainter objects. The maps that sound like breakthroughs today will look like rough drafts a few years from now, and more eyes are lining up behind it. Enormous ground-based telescopes with mirrors the size of a house will stare at the same regions of sky as James Webb, but in different wavelengths. Where the universe hides in infrared warmth, they will catch its tiny variations in visible and near ultraviolet light. Future gravitational wave observatories won't just hear collisions of black holes and neutron stars. They will start mapping the background, the low whispers stretching from early times like construction noise that started before the first cities were built. In orbit, the Nancy Grace Roman Space Telescope is waiting in the queue, a mission that roughly speaking will look at the sky like Hubble, but with a field of view hundreds of times larger, and with sensitivity to some of the same warm wavelengths as James Webb. If Webb is a pair of binoculars diving deep into one tiny patch of sky and finding wonders there, Roman will be more like a panoramic camera, revealing whole continents of the cosmic web at once. None of these instruments cancel the others out. Together they start to look like a set of senses the universe is gradually growing for itself. We're used to thinking of telescopes as human tools. But zoom out and a strange, honest picture appears. Galaxies created stars. Stars forged heavy elements. Those elements built planets, and on one of those planets emerged creatures who learned how to polish mirrors and launch them into space. Now those mirrors are looking back to an era when there were no planets, no creatures, no mirrors at all. The organism has reached a stage where it can turn around and look at its own childhood. Meanwhile, the list of questions on the table looks a lot heavier than the list of answers. Early galaxies with masses that don't fit the cosmic calendar. Supermassive black holes acting like someone hit fast forward on their growth. Knots of the cosmic web showing up on stage earlier than they should. Dark matter holding all of this together and never once getting caught red-handed. We only see its gravitational shadow. Dark energy steering the fate of expansion, whose effect we can describe but whose nature we barely touch. And layered over all of that, a different question. Are those layers of reality we've been talking about just a helpful metaphor to keep us sane in the face of ugly equations? Or are they a hint at something greater? Maybe our world, with its straight-line time, is just one floor in a cosmic building, a place where physics, information, and consciousness aren't separate. They are just different languages, describing the exact same process. Honest science doesn't rush to lock in one answer. It's used to living in in-between states. Today we sketch the universe as one massive calculation, tomorrow as a multi-layered network, the day after as something else entirely. These images are scaffolding to move forward with, not final portraits. And that's okay. You can think of each new telescope as one more eye. The universe opens. Hubble taught it to see its youth in visible light, bright, polished, poster-ready images. James Webb gave it night vision, pulling out faint, stretched-by-time glows. Radio telescopes are like ears, catching the whisper of neutron stars and the rustle of the cosmic microwave background. Gravitational wave detectors are a new kind of sense altogether, not depending on light at all, but reacting to ripples in space-time itself. Somewhere in that mess of noisy pixels, shaky measurements, weird plots, and too big, too early objects, this system might be slowly remembering itself. Not because it has a plan or a destiny, but because that's how complexity behaves. Sooner or later, any sufficiently intricate computation starts to contain a model of itself, like a program that learns to monitor its own errors, or a brain that starts thinking about how it thinks. We, humans, end up in the middle of this process almost by accident. No mission statement from above. We just happen to be good at asking questions and building instruments. And now the way we look at these images and what we choose to do with that knowledge slightly changes how the universe looks at itself through us. What matters is that this isn't a story that ends with a dramatic "here's how it is." It's more like a pause on a landing between flights of stairs. We know our maps of the early universe are incomplete. We can see that our tidy calendar starts to crack where James Webb shows us galaxies that are far too grown up. We sense that ideas about layers in a computing cosmos might turn out to be a useful wishing model or a beautiful illusion. We have to admit that terms like dark matter and dark energy are for now question marks dressed up as nouns. What stretches in front of us are whole branches of story. We could follow the line of dark matter, from the first hints of missing mass in galaxies to modern attempts to catch a particle that stubbornly refuses to leave a trace. That's a story about how we discovered an invisible frame inside the universe, and still don't know what it's made of. We could dive deeper into the vacuum, into what we casually call empty space between particles and galaxies. Modern physics keeps whispering that it's anything but empty. The most alive layer of reality, where things constantly flicker in and out, where energy and information are packed far denser than we're comfortable calling nothing. That's already almost philosophical territory. How can nothing turn out to be overflowing with possibilities? Each of those lines is its own film, its own floor, its own staircase you can climb and climb. Right now, we're standing in the one spot where you can see something simple and important. The story isn't over. It just changed scale. We're no longer telling a fairy tale about how nothing produced a world, and the world produced a person who understood everything. We're telling a story about a world that produced beings who are just starting to realize how much they don't understand. And this is one of those rare times when admitting your limits doesn't reduce you. It lets you be part of something genuinely huge. You can close the tab with the James Webb images, You can go back to your to-do list, your job, your alarm clock, tomorrow's errands. The cosmos won't blink. It will keep expanding, forming new structures, rearranging its layers of reality. Telescopes will keep circling in orbit. Antennas will keep listening to the sky. Scientists will keep arguing at conferences about what exactly we're seeing in those first deep fields. But in the background, one simple thought will still be there. We're never going back to a time when a picture of galaxies was just a pretty background on a screen. Now it's an invitation. An invitation to watch, to doubt, to argue. An invitation to ask questions not only of the universe, but of ourselves. Why do these stories pull us in? What actually changes for us when we know something about the distant past of the cosmos? How are we going to live, knowing that our home is a building with many floors and the elevator has only just started moving between them? You can shrug it off. You can say, big deal, another telescope, another theory. Or you can treat it differently. As the moment when humanity didn't just look at the stars but saw that behind them lie entire cities of light, a scatter of questions, and a strange, calming feeling. We really are standing at a threshold, not at a dead end. And maybe the most honest thing to say in the end isn't "this is how it all works," but "let's see what happens next." Because somewhere out there, in data that hasn't been processed yet, in missions still on paper and experiments still only scribbled on whiteboards, the universe is preparing new frames. And one of them might well be the beginning of the next story. About what dark matter is made of, or why the vacuum we keep calling empty might turn out to be the most crowded layer of reality. Which means that standing in your dark room in front of that small screen, you're not at the end of the movie. You're at the very beginning of a long, strange, beautiful playlist. The universe has only just started to play through us.